as it says in your program, and then there are some additional talks in the afternoon. So this is an afternoon talk, couple of talks, and then David will be in the mornings, and then there'll be other talks in the afternoons. There's a couple of other announcements. If you haven't yet registered and you need bits and pieces of paper and math and so on, I'll be upstairs after this talk, and you can do that. If you want reimbursement for your travel, and if I promise you reimbursing, we're all very excited. So here is David Ben-Zvi on Geometric Langlands.
Thank you. Well, I'd like to thank all of you for coming. I'm very excited and honored to be here. And I'd like to thank Balázs for all the great work organizing this. And OK, so I'd like to say a couple words about the program, the talks. So this is sort of, this is roughly the schedule in the abstract, and I'm hoping to roughly stick with it. So kind of as a rough overview, let me, sadly that's all I have. I was hoping to have something more exciting. But so the Geometric Langlands program is something like a Fourier theory for sheaves on moduli spaces of bundles on Riemann surfaces. So I'd like to try to explain what these words mean and why you would want to have such a thing, and what goes into it, and what applications and what kind of impact such a thing might have. So what I'd like to talk about today is sort of what do we mean by Fourier theory, and why do I want to talk about sheaves. And tomorrow I'm going to discuss some of the geometry of moduli spaces of bundles on Riemann surfaces. And on Thursday, I'm going to focus on the symmetries of these moduli spaces of bundles, which are the Hecke operators. Friday is going to be devoted to some exciting recent work of Kapust and Witten relating Geometric Langlands program to topological field theory. And finally, Saturday, I hope to have some talk about some applications, mainly applications to representation theory. OK, so that's the general plan. So let me begin by saying, by reviewing just the classical, someplace where all feel comfortable, classical Fourier theory of the Fourier transform. So how do I want to think of the Fourier transform, or slightly more generally, on Pontryagin duality? So what's the setting? We're going to be talking about here. So we have G is a locally compact abelian group, topological group. By the way, is this legible to everyone? Yes. Great. And let me know if I'm not speaking clearly. If you have a locally compact abelian group, so the examples, we took R, S1, the integers, etc. And so what do we study in Fourier theory? We study a unitary character. So we have a unitary character of G, which is a map chi from G to C star. Well, to really, I'm going to talk about unitary characters. It's a map to complex numbers of norm 1, which has the character property that chi of x plus y is chi of x times chi of y. So I'm writing G additively. So what do we do with these characters? The set of characters form, again, a locally compact abelian group, which we'll call G hat. This is the dual group of G, the group of characters under pointwise multiplication. And so let's maybe write a couple of examples of this. Actually, maybe that's not so wise. Let's go here. Is this still legible down there, or can people in the? OK. OK. So what's our examples are if we have so for S1, the characters. It's too high. So the characters of S1 are e to the I n x for n in Z, and the characters of R are labeled by, so these are the e to the I tx, where now t is in R again, and these are our dual groups. This is the groups of unitary characters. And so what do we do with this in Fourier theory? So the main idea of the Fourier transform is that characters span functions on G. So I'm going to think of these characters as complex valued functions. And the way I'd like to think of the Fourier transform is the idea that any function can be written as an integral of characters. Any function can be written as a linear combination in a continuous sense of these characters. So if I give you a function f of x, and I'm going to be a little vague right now about what class of functions I'm looking at. So if I have a function f of x, I can write it as an integral over the dual group of some function f hat of t times a character dt. So this is the way I like to think of the Fourier transform. And so let me just to write this a little more pictorially. I'm going to look at G cross the dual group. So this is something that has projections to G into G dual. So let me call these pi 1 and pi 2. And so I'm starting with a function f of x over here. And I want to write it in terms of a function f hat of t over here. And the way I do this is I take my function. So let me write the same formula in a different way. I take this function f hat, and I pull it out from this factor to a function on the product. Then I multiply it by this expression chi of x t. So what is chi of xt? Chi of xt is the universal character. So for each value of t as a function of x, this is that character. Okay? Does that make everything clear so far? Okay. So we have a character which is a function. So in our example, in the real example, this would be the function e to the itx as a function of x and of t. So this is, in that example, this would be r, the xr and the tr. That's what we're looking at. And we have e to the ixt as a function of the two variables. And so we take this, we multiply by the character, and then we integrate along pi 1. Okay. So this is how we want to think of the Fourier transform. So any function can be written as a linear combination of the characters where the coefficients are given by f hat. Okay. So now, let's see. So what are the key features of the Fourier transform? Well, maybe the first important statement is that this Fourier transform, so let me write it with a capital F, gives isomorphisms of function spaces. So to be a little more precise, for example, you have isomorphism between L2 of G and L2 of G dual, where the inverse is given by the same procedure up to some signs. So we have an isomorphism between L2 of G and L2 of G dual. So every function on G can be decomposed in terms of characters, and conversely, G is characters of G dual. So this is a symmetric situation, but I'm going to be interested in more general function spaces. So for example, if I have on R, I'm interested in something that's definitely not an L2 function, which is the function to e to the I lambda x itself. And this function corresponds under the Fourier transform to a delta function at lambda. So this is kind of the main point, is that delta function at a point t, so points of G dual correspond in this way to characters of G. What are the other key features? Another key feature is that, let me interrupt myself to say that I'm going to have notes for all of these talks. It'll be posted during the week on my webpage. So if you don't feel like trying to copy this, then they'll all be available online. Okay, so what is another key feature? Key feature is that the Fourier transform, it diagonalizes the action of the group of G on functions on G. Functions of G. So how do we think of this diagonalization? One way to say it is that if you take...
What is the action? You talk about the action...
by translation. I'm going to act by left translation on function.
It's the regular representation.
The regular representation, that's right. So if I look at the action by regular representation, and then the irreducible representations appearing here are the characters,
Yeah. Okay.
and those correspond to points on the other side. So the way I want to summarize this is that if you take various operations on functions on G, which are, for example, convolution or translation or differentiation on the functions on G correspond under the Fourier transform to multiplication operators. So the idea is that we're going to take these kind of things coming from translation on the group, and they get taken to just multiplication. That's our version of a diagonal matrix. So for example, if you convolve with a function G, this corresponds to multiplying by the Fourier transform of G. And ddx, for example, differentiation with respect to x, in the case of R, corresponds to multiplication by t, etc. Right.
You want to be self-adjoint. No, the t is all right.
The t is all right.
An I or a minus sign.
Right. So let me write mod I.
Yeah. ddx is not self-adjoint.
Thank you. Okay, so that maybe gives an indication of the level of detail. Okay, so this is the picture of how I want to think of the Fourier transform. And what we'd like to do throughout this week is find an analog of this picture, of all the aspects of this picture, for a much more complicated space, which is the moduli space of bundles on a Riemann surface. So we're going to replace this locally compact abelian group, so for example, replace the real numbers, by the moduli space of bundles on a Riemann surface, which we'll discuss tomorrow. And so so there are many questions to ask. What do I mean by that? How are you going to, in what sense are you going to replace a locally compact abelian group? And the first thing I'd like to do is to explain what I mean by functions. So this is going to be kind of our main obstacle to coming with a Fourier theory, is what do I mean by functions? What class of functions am I looking at? Is kind of a maybe an geometric version of this story, of this kind of harmonic analysis. And this is what the geometric Langlands correspondence is going to do in a very specific setting. So you can ask, first of all, in harmonic analysis, we have lots of interesting function spaces, very rich function theory. What are we going to do in algebraic geometry? So first of all, I should say, what are our spaces that we're looking at? What kind of objects am I looking at? So the first kind of thing would be affine algebraic variety. Algebraic varieties. So this is, and for purposes of this week, everything is going to be over the complex numbers, just for safety. So what is affine algebraic variety? We're going to look at some subset of affine n space over the complex numbers, which is cut out by polynomial equations. Cut out by polynomials. And in this context, we have a notion of functions. We can look at polynomial functions on x. For example, x could be the affine line itself. That might be a nice substitute for the real numbers. So we can, we have, let me denote it by, I'm going to denote it either O of x or just write it C of x. These are polynomial functions, so just the restrictions of polynomial functions on affine space. These are going to be polynomial functions on x. So that's a function space. You might already complain that this is a very kind of weak, very, very small and kind of meager function space from the point of view of Fourier theory. From the point of view of Fourier theory, I have a lot more different, I have L2 functions, I have distributions, I have Schwartz spaces, I have lots of more interesting spaces. And just looking at polynomials is probably not so rich as a context to do harmonic analysis, but at least it's something. The trouble comes when we go beyond, oh, that already vanished. So the problem is going to be when we try to go beyond affine space. So if I look at, so what are more general spaces? So the more general spaces that I'm going to want to look at, so what do I mean by a space in algebraic geometry? It's something that's covered by affines. So it's going to be given by, so it's some space which is given by gluing affine varieties in some ways. So what do I mean? So let's just to write it kind of schematically. I have a space X, and the way I'm going to write the space X is it's going to be covered by a disjoint union of affines, where these are, over some index set, these are affine varieties. And it's glued by some relation. So there's some gluing laws on the overlap. So I have these. What do I mean by the overlaps? I have, over a pair of indices, I have, let's say, uij, which is the, that's a bad idea. uij, which is the intersection or fiber product, uj. So that's my intersections. So what I'm going to mean by, and so I think of these as the kind of generators, and these are relations. So I'm going to be talking about a very general class of things that go by various unpleasant names, like algebraic stacks, but the kind of, or maybe very pleasant names, depending where you're from. But the general picture is everything that I'm going to be talking about is some kind of space, for example, a scheme or a variety, something that's covered by affines. And everything I'm going to do is going to be by looking locally. And in local picture, I'm just going to be some polynomial ring. OK, so this is the kind of spaces. So the kind of example we would have is just take an elliptic curve. So maybe a good example to keep in mind is just take a cubic curve in the projectives plane. And that's covered, you can cover it by affines, by two affines, for example. OK, so that's a space we're going to keep in mind. So now the question is, what are functions on this? And what you immediately run into the trouble is that if you look at polynomial functions on something projective, for example, an elliptic curve, there are only constants. So in general, what's going to happen is you look at functions on these UIs, and you're going to ask them to agree on the overlap, and you'll find that there are no. So generally, we have no non-constant functions. So this is a very bad situation if you want to talk about some kind of harmonic analysis. So what we're going to try to do is we're trying to think of substitutes. What are we going to do? So there are many different answers you could put as substitutes for polynomial functions. And so what are some examples? Well, if you have an elliptic curve, you might think one thing to do is not look at functions, but sections of line bundles. And so one kind of thing you could do is look at sections of various line, or more, if you're more ambitious, or more general vector bundles. So a section of a vector bundle is some kind of twisted version of a function. So we might look at not globally defined functions, but twisted functions. Another thing we could try to do is, if we like these delta functions that appeared over here, we might think that a good substitute is things like functions or twisted functions on subvarieties. So for example, we might take a point and look at functions on the point. And so that gives us, so now this gives us various classes of things to look at. So what do these kind of, and you can come up with, of course, many other answers. And there's something that all these notions share. These notions share two key properties. So one property is locality. A notion of a function is a local object. Function is something that I can, it's determined by restriction to each open subset. So a function is something that should be defined in terms of local data and glued in an appropriate way. Okay, so that's common to all of these things. And the second feature that I'd like to emphasize is linearity. Namely, if I give you a function, I can multiply it by another function, or more specifically, I want to multiply by polynomial functions. So I can multiply any such thing by a polynomial function. Now you might complain, I just said there weren't very many polynomial functions. But I could do this, but I have part one, locality, so I can look locally. So I look at my notions of function, and on any open set, I can multiply it by open functions on those open sets. And there, at least, I have a bunch of polynomial functions. So these are the two properties. And so now I'm going to kind of make a leap. And this is a leap that's sort of necessary for the geometric Langlands program, but necessary for many other things. I'm going to say that what I care about is not the actual function themselves, but the modules they span over action of polynomial functions. So I'm going to say I'm going to replace all these different notions of functions, these various notions of functions, by the modules, which are, let me say, O of ui modules. They span on each open set. So in other words, given a function f, I'm going to replace it by, over each of these open sets I can look at all of functions, polynomial functions, times f. I'll call this m sub I. Okay, so this is the new kind of gadget I want to replace. Instead of looking at functions, I'm going to look at these modules. Over each open set, I have some module over functions, and these modules are now required to glue instead of the functions to glue. Okay, yes.
Polynomial functions that you want, should I think of them as sections of algebraic?
The polynomial functions are going to be sections of just the trivial vector model. They're just going to be holomorphic algebraic functions on each open set. But I'm going to look at modules over those polynomial functions. So the idea is that I'm going to replace a function by such a collection. So this is what such a thing is what we'll call an OX module, or a coherent sheaf. So I can make various requirements on what exactly kind of collections of modules I'm going to allow, and I don't want to get into the details of this. I'd like to just say that my idea is going to be, instead of having a function on each open set, I'm going to have a module over polynomial functions on that set. And I think of that as a substitute to this would-be function. Does that make sense? Okay. So this is kind of the kind of leap. So I'm going to use this word coherent sheaf kind of as a black box to denote this kind of thing. It's kind of a substitute for functions. And so what we're going to do is we're going to make this leap where we're going to replace function spaces by the collections of these modules over polynomial functions. And throughout the week, hopefully, we'll see many. This might not seem sufficiently motivated at this point. We'll see a lot of places where this kind of assignment, this kind of replacement comes up, and why this is a useful way to think about functions. So the kind of leap I want to make is that if I look at spaces of functions, the kind of function spaces that appear in harmonic analysis, they're going to become, well, we're going to look at these modules over rings, or these sheaves. So this is functionally what I mean by a sheaf. It's just going to be, to each open set, I have some vector space with maybe some additional structure, and they glue together in a nice way. So I'm going to replace, and now these sheaves no longer form, these modules don't no longer form just a space, they form a category. Categories of modules. So this is going to be the kind of assignment. And so maybe one way to motivate a little better is that we look at these function spaces, we have also, for example, inner products. So suppose you have a function space with an inner product. This becomes, collection of modules has its structure of a category. In other words, we have, if you have M1 and M2 modules, you have a vector space which is hom from N1 to M2, which are just maps of these modules that preserve the action of polynomials. So this is somehow an analog of inner product spaces. But there's clearly a lot more structure, and these things are a lot more complicated than, in some ways, than vector space of functions. But this is going to be the kind of analogy we're going to stick with. So, okay, so how should we think of these categories? Well, what kind of things are these categories? So we have these objects. So we have these objects which are our sheaves, or our modules. And for each pair of objects, I can look at the collection of maps between them. So, and these vector spaces, these hom vector spaces, in particular, these are C vector spaces. So, so how do I want to think of a category? What is a category? I want to think of a C-linear category. So this is C-linear, meaning all the homs are vector spaces. A C-linear category I want to think of as just a partially defined associative algebra. So what does this mean? We have a bunch of arrows, these homomorphisms, which we think of as the elements of an algebra. The only problem is we can't compose, say, this arrow and this arrow. We can only compose them when the tail and the head meet. So you can think of this as a kind of an algebra with many objects, or a partially defined algebra. So maybe another way to make this leap is to say, I'm not really completely abandoning function spaces. I'm replacing them with some kind of algebra. This algebra happens to be partially defined, and it's associative. So this is another key problem. This is not a commutative algebra, like we had in polynomial rings. This is a noncommutative algebra. So this is, in some sense, a step of noncommutative geometry. We're going to replace thinking about the space X and this commutative rings of functions on it by these kind of global objects, these non-commutative partially defined algebras, which are these categories of modules. Okay. One can also say that, so in fact, if you don't like these partially defined things, you can really make a single algebra out of this thing. So in fact, this category of OX modules is basically the same as A modules, where A is some associative algebra. And how do we define such an associative algebra, at least in slightly caricature way? I want to say I'm going to take functions on each of my open sets. So I have my ui, my uj. I take the collection of functions on each of these open sets, and I'm going to add to them some gluing maps coming from the overlap data. So I'm going to make something it's called a groupoid algebra, and it's some kind of matrix algebra where I think of these as my matrix entries and the functions of u on the overlaps as the kind of matrix multiplication. These are the entries of the matrix. So what you can make, this is kind of an Alain Kohn style approach to thinking of these spaces. We're going to take the functions on each open subset, and we're going to glue them together into a non-commutative algebra by adding these relations coming from the overlaps. So there are many ways to think of this, but this is going to be my first leap. So are there questions about this kind of?
What is the groupoid?
So there's a groupoid coming from the gluing relations. So the objects are given by the UIs, and the morphisms are given by UIJs with the two maps. So I just make a groupoid algebra, which is, so for example, the easiest case, if I have an affine space and I want to quotient out by a finite group, I just take functions on this affine space and kind of smash it with the group algebra. So the group algebra is giving the gluing laws of how to glue the different open sets. And then I get a non-commutative algebra, which has the same modules as the quotient. So modules over that non-commutative algebra are just these coherent sheaves on the quotient. So that's a kind of the one way to think of doing these gluings. So since everything I'm ever going to look at is of this form, it's a space defined by some gluings, you can think of doing these gluings in any language you want. And one way to do them is the language of noncommutative geometry. I'm going to use lots of different ones through the week. Right now I'm looking at the category of coherent sheaves. So my category is the category of coherent sheaves, but I want to think of this as modules for some kind of noncommutative algebra. Okay.
Is that a true fact? I mean, if I take a project,
yeah, that's a true fact. I'm being a little sloppy about algebras versus coalgebras in this picture, but it's a true fact that if you take a projective variety, for example, then coherent sheaves on it are always modules over an associative algebra.
What is that?
Derived. Sorry.
Let's say we're on a projective variety.
Right.
We can talk about coherent algebraic sheaves.
Right. So
What is the algebra?
So the algebra is going to be endomorphisms of some generator. So the statement, I'm probably lying a little bit in this context. I want to talk in the derived context, but it's a noncommutative algebra. It's going to be so if I have an abelian category, I can embed it in terms of in modules over a generator. I found a generator for this object, and I look at modules for that generator, endomorphisms of that generator.
Are you saying that to any projective variety, there is intrinsically associated a non-commutative algebra?
Up to Morita equivalence.
Okay, up to Morita equivalence, there's a non-commutative algebra such that the category of certain sort of modules of that algebra is equivalent to the category of coherent algebraic sheaves
Yes.
on the projective variety?
That statement is literally true in the derived category.
Oh, you might have to go to derived.
Yeah. Yeah. So which is my next step. So this is okay. So this is sort of our next problem is going to be passing to derived categories. So where do derived categories come from in this context? I want to motivate why I want to pass to derived categories, and there are many ways to motivate that. One way I'd like to motivate is what do we actually want to do with these spaces of functions? What we want to do with them is some version of convolution. We have this, or some version of operators like the Fourier transform.
I want to ask a very naive question. I mean, the world's simplest projective variety is just CPN itself.
Absolutely, right.
What is the noncommutative algebra?
So it's so I apologize. This is a statement. I'm going to switch to derived categories, and I'll motivate it in a second. But for CPN, I look at the line bundles O of 1, O of 2, up to O of n, and this is a collection of line bundles on this variety, and I want to look at the direct sum of all of these line bundles. Let's call this E. So that's a vector bundle on this variety. And I want to look at the X algebra, the endomorphisms of E. So this is a differential graded algebra. And Bailenson proved that this derived category of projective space is equivalent to modules over this particular algebra. This algebra has a much simpler picture to draw, which is it's the algebra associated to a quiver, where I'm going to need some multiple number of arrows. So it's an algebra associated to a particular quiver. So in the case of P1, there's an algebra. So I have two, I think this is called the Kronecker quiver. I have two objects and two maps between them. And I look at an associative algebra generated by these arrows. And Bailenson's theorem in this case says that this derived category of sheaves on projective space is equivalent to modules over this differential graded algebra. And so then there's a generalization of this. It's a general fact for any of the kind of objects I'll be talking about. So we can always think of these sheaves as just modules for some differential graded algebra. So as I've already slipped in the word derived. So now let me try to motivate why give some excuse for that. The motivation I want to give for doing derived categories is that what we want to do with these, we want to do things with these function spaces. We don't want to just construct them. And the main thing I want to talk about this week is convolution. This is the main operation we'll be doing with functions. So what do I mean by convolution? So let's just look at the simplest example, which is a finite set. So this is going to be a long way from the varieties I'm looking at. So suppose Z is a finite set. Let me look at functions on this finite set. So I can just identify that with Cn. OK, so now I want to look at functions on the finite set Z cross Z. And I want to identify functions on Z cross Z with n by n matrices, or if you'd like, endomorphisms of Cn. And one way to say this, so this is kind of silly, but I want to draw it by the same kind of picture that I drew for the Fourier transform. I take function, so here I have a vector in Cn, and here I have a matrix. And I'm thinking of my matrix as a function on Z cross Z. And the action of a matrix times a vector I can write as I push forward along the second factor the pullback A times the pullback of V. So this is just a silly way to write down matrix multiplication. This is another way to say if I take A dot V I is the sum of Aij Vj. So, but the point is that this picture is going to be the picture that motivates all of our operations. So maybe one exercise is to write down a matrix multiplication in the same language. So if you want to write down the multiplication of two matrices, matrix multiplication, you look at functions on z cross z cross z, and you use there are going to be three different projections to z cross z. And so maybe that's a good exercise to figure out to write matrix multiplication in that language. So how are we going to use this more generally? I want to replace finite sets by some kind of spaces. And so now, in order to do this, I discover the one operation that there's no problem in talking about a function on one factor, pulling it back, multiplying it by a function on the product. The one thing I have to think about is how to do this push forward. So to do this push forward, I need to have some notion of integration. So I have pi to push forward is some kind of integration along the fiber. So if I'm going to have a nice theory of functions and I'm going to be able to write down some version of multiplication, I need some version of integration along the fiber. So if I'm looking at spaces, I really want to have not functions, but I'm going to have in the background, I want to have some kind of measure in order to be able to integrate. But let me gloss over that. So let's look in a context where you have a measure. And we find this picture that if we have a vector space of functions, operators on functions on Z, where Z is now, say, a nice measure space, are given by kernel functions on Z cross Z. So just take a function on Z cross Z, and I do the same operation. And if I'm in a nice enough context, all operators on this space of functions will be given by functions by integral kernels, by doing the exact same formula. So I want to think the operators I'm going to look at are all going to be some kind of matrices. So how do we do this? So what are different contexts to do this? We can say what we're really talking about in maybe a topological version of this is that I'm not really going to be interested in functions, but I'm going to be interested in something like differential forms or something like cochains. So really, instead of functions, if I don't have a measure around, I should think that I'm looking at something like differential forms or some kind of cochains. And then I'm going to have an integration theory. So really what we want to say, we want to replace functions by any kind of theory which has the three operations we need with pullback, product, and push forward. So what's an example of this? So an example would be if Z is, say, a compact manifold or compact-oriented manifold, then I can look at the cohomology of Z as my version of functions. And then by the Kuhn theorem, I get that if I want to write operators from cohomology of Z, or more generally, if I have cohomology of maps from the cohomology of X to the cohomology of Y, where X, Y, and Z are smooth manifolds, I can realize that as in terms of the cohomology of X cross Y, and by the same picture. So I take X cross Y, and I have X and Y, and I'm going to take a cohomology class here, and I'm going to take, so it's again the integral along pi 2 of some cycle across, so pi 1 star of C times some cycle on the product, some cochain on the product. Okay. So this is kind of the general procedure. In topology, we know we have for smooth compact manifolds that we can realize operators from cohomology of X to cohomology of Y by things on the product. And this is the kind of operations we're going to be doing all week. So now I want to go back to my context of sheaves, or these coherent sheaves, and say, how am I want to have some theory that I can do these integral operations in. This is going to be essential to having any kind of version of Fourier theory or harmonic analysis. And what we find is that we can't use just these coherent sheaves. We have to, because the coherent sheaves were somehow substitutes for functions. Now we want to replace functions by things like cochains. So how are we going to do this? I'm going to replace, instead of having vector spaces everywhere, I'm going to replace vector spaces by cochain complexes. By cochain complexes. So instead of things of the form ci plus 1, ci plus 2, where these are all vector spaces and d squared equals 0. So that kind of as a general rule, every time before I had a vector space, I'm now going to have a cochain complex. And I'm going to look at these up to refinement. So what's refinement? Also, this is quasi-isomorphism. I'm going to think of, if I give you a space X, I can think of assigning to it cochains on X as some version of functions. But what do I mean by cochains? You might have lots of different theories of what you mean by cochains. So someone might say singular cochain. Someone might say simplicial cochains for one triangulation or another triangulation. There are lots of different versions, and I want this to be well defined. So I want to say that for example, if I take a triangulation, I can look at simplicial cochains for that triangulation. I don't want to care which triangulation you take. So if you refine the triangulation, I want to have the same answer. So this is going to mean I'm going to look at these. If I have such a cochain complex, what's the algebraic version of refinement? It's quasi-isomorphism. So if I have two such things, and I have a map between them, which commutes with the differentials, and so let's call this phi. So phi is a quasi-isomorphism if it induces an isomorphism between the cohomology of C and the cohomology of D. So this is a kind of a funny world that we're going to look at. We're going to say we're going to replace vector spaces by cochain complexes, but that's a little too much. We don't want to remember all this kind of information. We want to care about them roughly only up to their cohomology. So if you have two cochain complexes and a map between them that identifies the cohomology, we'll think of them as being the same. So how does this? So I should note that for the rest of the week, all of this is going to be absorbed in a big black box. And so there's going to be I'm going to introduce the derived category, and it's going to be a black box, and so we don't really need to stare at it too deeply. But we should just know at least what kind of objects we're looking at. So let's continue. We have vector spaces became cochain complexes, and before I have so what next do we have? We have associative algebras. What becomes of associative algebras? They become differential graded algebras. And so instead of having an algebra in vector spaces, I'm going to have an algebra in complexes. So it's going to be a complex of vector spaces with a multiplication. So what else did we have? We didn't have algebras. We had these partially defined algebras, which were these categories. So before we had these C linear categories, which I thought of as associative algebras which are only partially defined. So we're going to replace these C linear categories by differential graded categories. What does this mean? This means exactly apply this process. In other words, every time you see in a category you saw a vector space of Helms, now we'll have a complex of Helms. Okay. So I'm just applying the same process. Every vector space becomes a complex. And so if you have a category, you can think of a category where you have objects and the Helms between them. Instead of just having a vector space of Helms, I have a complex of Helms. Okay. So this is the world of DG categories. And this is the world where we're going to work. So again, I want to think of what is the DG category. It's just a differential graded algebra which is partially defined. That's all it is. You just have a bunch of objects, and you can only compose some arrows. Only arrows that match up can you compose. But it's no worse an object than a differential graded algebra. And so how does this have to do with our function theory? So if X is an algebraic variety, or one of these things glued from affine subsets, I'm going to assign to it this object, which I'll call dxo. And this is going to be the main star of this week. So what of DXO? This is the category of complexes of sheaves, or these things we had before, these O modules. So things of the form F dot, which is Fi plus 1. Okay. So on each open subset, instead of giving you a single vector space, I'm going to give you a complex of vector spaces, which are modules for functions on each open subset. So on each open subset, you have an action of polynomial functions on that subset. And again, I'm only going to care about these things up to some kind of refinement, so up to quasi-isomorphism. So, so this is going to be, and I'm going to think of this as a differential graded category. It's going to be some kind of differential graded associative algebra with partially defined multiplication, where the objects are given by these complexes. Okay, so this is sort of the problem with the geometric Langlands. At some point, you have to make this leap. So you have to accept, somehow, come to terms with the idea that what we're going to be doing all week is a lot of things that are very familiar from some kind of harmonic analysis, but every place we're going to just get rid of functions and we're going to replace them by something like this, by some kind of derived categories.
And this one example of function space?
Yes, so this would be an example of a function space. So for me, a function space is now going to be a DG category.
But
This is an example. So to any variety x, I'm going to assign this. This is going to be my functions. This is going to be my functions on x. So in my first version of the notes, I wrote fun of x for this. Then I thought it was a little too abusive. But this is I'm going to really think of this as functions on x. Right. This is kind of a general principle that every time you have a vector space, I'm going to make it a cochain complex. So before I had, but here I have both on the level of objects and the level of Homs. My Homs were linear C vector spaces. Now my Homs will be complexes. My objects were modules. Now my objects will be complexes of modules. Right. Yes. No, I have not, and that's what I'd like to do now. So why are we doing this?
What is that? If I have two complexes of sheaves, what is the
So I'm going to look at, so if I have just two complexes of vector spaces, if I give you two complexes of vector space, I can make a complex of Homs. So you look at all Homs of various degrees, and it has a differential on it. So that's what I mean when I look at a category of complexes. Why are the Homs themselves complexes? Because of that. And so here, again, the Hom of two of these sheaves, there's going to be a big Hom complex. So on each open subset, you look at morphisms of any degree, not necessarily commuting with a differential, and there'll be a differential on that. So what people usually mean when they, so this is again a big abuse of terminology, what people usually mean when they say derived category is H naught of this. So in other words, the Hom between two sheaves is just going to be morphisms of chain maps of degree 0 modulo exact 1. So, so this is not exactly the usual terminology, but it's quite close. Okay. So, so why is this good? What was our point in doing this? Our point in doing this is having an integration. So my claim is going to be that we can now integrate. Just like we can do in topology, you can integrate cochains, where if your cochain happens to have the wrong degree, you go to 0. You can integrate cochains without having to have a measure. And this is one of the advantages of doing this. So, so there's got a theory of integration. So let me just do maybe an example of this. Maybe the silliest example. How do we integrate to a point? So this is one of the points of having derived categories is I'm going to have integration from a point. So what is my integration map? Well, it should now take a complex of these sheaves on X and give me a complex of sheaves on a point. In other words, a differential graded vector space. That's my integration. So how do I integrate? Well, you take cochains. So you do integration the same way you would. So for example, what I can think, what is my sheaf on X? For example, I can take the constant, the sections of the trivial bundle. And then my integration will be just take cochains. So if I have a sheaf F, I'm going to assign to it cochains on X valued in F. This is the integration method, and this is what I'm going to call the push forward of F. So now you ask, what do I mean by cochains? And the point is I don't have to tell you. Because you can decide, so here this could mean, for example, I can take check cochains. So I have F is defined in terms of this open cover on this cover UI. And I can do check cochains on the cover. Or if you're in a complex analytic context, you can do Dolbeau cochains. So here I'm thinking of F as just, for example, a holomorphic vector bundle on a complex manifold. And the corresponding sheaf is, or rather I'm looking at its sheaf of sections. So how do we push this forward to a point? If you give me a holomorphic vector bundle, I need to give you a complex of vector spaces. And what am I going to give you? Take the check cochains, or take the Dolbeau cochains, or take some kind of simplicial cochains for some kind of triangulation. You take your favorite theory of cochains and you do it. You see what it gives you. And since I only care about this differential graded vector space up to this kind of refinement, this is going to give you a well-defined answer. So I'm really going to think of it in terms of a check picture. But this is my version of integration. So more general integration. So in other words, integration of sheaves is going to be given by taking check cochains along fibers. Okay. So I want to, again, this is a sort of the most technical part of the week in the first lecture. So you'll have to kind of trust me that maybe this is a good thing to do, and hopefully we'll see motivations for why this is a good operation. But I want to basically treat this as a black box, and I want to say now that I'm going to treat this derived category, DXO, as a theory of functions.
If we have a complex of sheaves,
Right.
what do we have, a bicomplex?
Yeah, so you have a total complex, and you totalize this complex. So if you like, there's a spectral sequence. Right. So
Why don't you just take global sections of the sheaves?
global sections is a good thing to do, but I need to include all of the higher cohomologies of this. So this is somehow the operation that's going to be well defined. So if you'd like, my initial guess is indeed take global sections. And then I'm taking the derived functor of this. I just want to say I want my answer to not depend on refinements of my sheaf. And that's the whole motivation. Replace your sheaf by any of its other refinement, any resolution of it, you should get the same answer. And that's what the derived functor is. So all the functors I write will be derived functors. They're functors living in this world. And so just to kind of claim that I have a good theory of functions, let me, I guess, end by saying one kind of property, that this theory that to an algebraic space assigns this funny object, the space of functions, I want to say is a good function theory. So what is a good function theory? And for me, the main point of a good function theory is it's going to have this property of integral kernels, or matrix multiplication, that operators should be given by matrices. So this is captured by a theorem. The strongest form is a theorem of Bertrand-Toine, or the versions of weaker statements by Bondal and Orloff. But let me just, what this says is that if I want to look at functors, so this is slightly paraphrased, but it says that if I look at functors from derived category X to derived category of Y, so X and Y are two of my spaces, are given by derived category of X cross Y, given by integral kernels. In other words, every functor has and by functor there's some notion of continuity that I'm suppressing. In other words, I take X cross Y, I have projection onto X and to Y, and I have a complex here, and I have some integral kernel, which is a complex here. Then I'm going to send F to, you first pull it up along this first factor. So in other words, you think of f as being a function on x cross y, not just on x, which doesn't depend on y. So I guess I should. I take this sheaf and I multiply it by this kernel. So now this is something I needed for my theory of functions, is that I can multiply. So here I have the tensor product of sheaves. So I have these modules over polynomial functions. I'm going to take their tensor product. And if you're keeping track, this is all in the derived world. I'm going to take this product, and then I'm going to integrate along the fibers. So in other words, I just take the same kind of operation I did in the Fourier transform, or just, if you'd like, this is just matrix multiplying by a matrix. And the claim is that anything you want is given by such a matrix operator. So this is, for me, saying that we have a theory of functions that that behaves well. Okay. Are there questions? Okay. Yeah. So this is again, this is a dx of O is not what is called the derived category in the literature. It's a differential graded enhancement of it. So this is a differential graded category made of complexes of sheaves with the quasi-isomorphisms inverted. And
Is this theorem valid also for such categories?
the theorem is valid, in fact, only for such categories. So one of the reasons to pass to this, in fact, maybe this theorem and its precursors are the main motivation for working in this language. Well, one of many motivations, I'd say, for working in this language is that this is not true for the usual derived category. This theorem is just false for the usual derived category, but if you have the right theory of functions, then it's true. Okay. So again, let me just emphasize that for the rest of the week, I'm going to basically treat this derived category as a kind of black box. It's something that I think of it as a space of functions. It has nice properties, in particular this kind of results. I can think of, and all the operations I'm going to do are all going to be given by these kind of Fourier kind of integral transforms. So after the break, I'm going to give you some examples of, well, in fact, the first example of this, the Fourier-Mukai transforms, and continue from there.